Dear students, welcome back. We have reached section 5.2.3 and we will continue with a financial mathematics application. We will look at the discounted portfolio process, but first let's summarize what we have done so far. So let's first start with the setting. We have a probability space, omega fp, event space big omega, filtration script f, and probability measure p. And of course, we have a Brownian motion, Wt. Little t goes from 0 to capital T, which is the end of a financial contract. So the final time of a financial contract. And our script f, the filtration ft, where t, little t, also runs from 0 to capital T. And we were given a price process, right? This is in the summary, we had this price process and it looked as follows. T is equal to S0 times e to the power, the integral from 0 to t, sigma s d w tilde s plus the integral from 0 to t rs minus 1/2 sigma square s ds. And see particularly this r here. This is our price process, the price process under the risk neutral measure, p tilde. And we also had a discount process, d, capital D, dt, the integral from 0 to t of e to the power minus the integral from 0 to t, capital Rs ds. Rs is our stochastic interest rate. And when this is just a constant interest rate, we end up with our familiar setting like e to the power minus r t minus t. The expression that we have seen in the very first lecture, and we have seen it more often. That is for constant r. Moreover, we had a theta function defined, theta t, and it was defined as alpha, the mean rate of growth, the mean growth rate of the stock, minus rt, the interest rate, divided by sigma t, the volatility. And we use that to change the measure from p to p tilde. And again, alpha, the growth rate of the stock was considered to be bigger than r, because we would expect that an investment in the stock is only worthwhile when the payoff is larger than putting money on a bank account, is larger than just receiving interest rates. And this change of measure to p tilde, for that we used dp tilde is zt dp, or dp tilde is z dp. Zt was sometimes abbreviated by just a z. And in particular, zt with little t as the argument was defined as the exponential function with as exponent minus the integral from 0 to t, theta u dwu, minus 1/2 the integral from 0 to t theta square u du. And in this setting, the setting of a price process, a discount process, a function theta, and a measure change function zt, we have shown a couple of properties for all these processes, and we summarize them here. The first one is that zt, little t between 0 and capital T, that is a martingale under P, under measure P. Secondly, we have seen that W tilde T, which was defined as Wt plus the integral from 0 to T theta SDS, that is in fact a Brownian motion under P tilde. We have also shown that. Thirdly, the discount process, the discounted stock process, denoted by capital DT ST, that was equal to D0 S0, and the values at time 0, plus the integral from 0 to T, sigma S, DS, SS, DW tilde S, and again, little t from 0 to big T. And we have seen that particularly this discounted stock price process, the process that we are particularly interested in, that is a martingale under P tilde. And because of this fact, the fact that the discounted stock price process is a martingale under P tilde, that makes that we call P tilde the risk neutral measure. So the discounted stock process is a fair process in a way. And so in terms of the conditional expectation of the value at time t, given the filtration at time s, that is at best, the best that we know is the value now, so that is DSSS. So due to this fairness property, we call P tilde also the risk neutral measure. Now, under P tilde, we have seen in the previous slide, the mean rate of return of the stock, alpha t, has been replaced by the interest rate R. Let's go back just to verify this one more time. Here we see clearly appear RS and not alpha S as we had before. So we are under the P tilde measure, and we also have DW tilde here written down here. So this is the stock price, the price process under the P tilde measure. And there we clearly see that, that R replaces, in fact, alpha. Now, what we'd like to show in this lecture is that under P tilde, the discounted portfolio process is a martingale. And remember the portfolio process, we had X, capital XT, and we have subdivided that portfolio process in a part that we invested in stocks and a part which we invested in the money markets. So that went as follows. We had this portfolio process, and typically the notion is that as follows, this portfolio process is like a hedge process. The writer of an option sells the option to the holder. For that, the writer receives a premium of the option. And that premium is based on the fact that the writer wants to buy a portfolio process, and this portfolio process changes all the time from time step to time step. This changes in such a way that this portfolio process is equal in value to the option. So when at the end of the time the option is in the money, is worth money, then the writer has the money or has the opportunity to fulfill his or her obligations. So that is a bit the notion. So we have this portfolio process, and later we will couple it, we will connect it with the option. So here you see two pieces, XS of XT is composed of two pieces, delta TST, delta stocks, which are, so delta stocks, so this is money invested in the stock market, and X minus delta TST, that is a piece that is invested in the money market. The remaining part, together they make X. This part is invested in the stock market, and the remaining part is invested in the money market. So an amount invested in the stock market versus the amount invested in the money market. And we also have the dynamics for the process, the portfolio process X. And those are written down as DXT, and DXT is delta T DST. Delta T is a number, time-dependent number of stocks. Delta T DST, and the remaining part is invested in the money market. So XT minus delta TST times RDT. If you have a money market, this grows with interest rate, with the amount itself, and with the time period dt. Now for DS, we can substitute the dynamics that we have already found, and these are the dynamics under measure P, so with alpha and dW. So we do that in the next line. So that is in fact delta T times DST, which is alpha T ST dt, plus sigma T ST dWt. That is all multiplied by delta, plus xt minus delta T ST RT dt, and that is just copied and that is written over here. Now we can collect the dt terms, and we first write down xt rt dt. We put that up first, and what's remaining in the dt terms is a term here and a term here, in fact. And we recognize a delta here and an s here, and we also recognize a delta here and an s here. So what we see here is alpha t minus rt, and then multiplied by delta t st dt. And here we also have a sigma t, a delta t, an st, and a dwt. So let's write that down. Here we have the first term, rt xt dt. Then this term that we just mentioned, alpha t minus rt times delta t st dt, plus sigma t st dwt. Hey, this delta is missing. All right, times delta t. And then we're okay, we're good. Now we have that change. We have this theta function, theta t, being equal to alpha t minus rt over sigma t. So actually alpha t minus rt we can replace by theta t times sigma t, and we do that in the next line. So we make use of this identity. And then we write dxt, is the first one is just copied. It's rt xt dt. And here for this we use sigma t theta t times delta t st dt. And the remaining part, so with delta t here, the remaining part is in fact sigma t delta t st dwt. Now with these last two parts, we can take out sigma, we can take out delta, and we can take out s. And then what we recognize here with this term here, this term here, and this term here is that we, in fact, so when we take that out of the brackets, we see that we have dw tilde t remaining. So we can rewrite that, copy the first part, and then this is nothing but sigma t delta t st times theta t dt plus dwt, and that can be written as dw tilde t. So these are the dynamics of our portfolio process. But again, as you may realize, we are not interested so much at this stage in the portfolio process itself, but more in the discounted portfolio process. So we look at the change in capital DT XT, the change in the discounted process, and which theorem, which rule do we use for that? Well, you can guess it, that is the Ito product rule. And that is on the next slide here. We use the Ito product rule and we copy it here for convenience. The change in discounted portfolio process, the D of capital DTXT, by means of Ito's product rule, that is the discount process times dx, xt times the change in the discount process, plus the change in the discount process times the change in the x in the portfolio process. This is just a copy of Ito's product rule, and we will substitute the terms that we know. Particularly, we have just derived dx. For d, the change in the discount process, well, that is minus rt dt small dt, so minus the interest rate at t, the discount at t times dt. And this term here, the change in discount times the change in portfolio process, well, this one goes with dt, as we see over here. So whatever comes here, the dw term gives us the cross variation, which is equal to 0, and the dt term, which also may remain here, that gives us dt squared, and that is also equal to 0. So in fact, this term will cancel out. We won't be dealing with that. So here we substitute dx, and here we substitute the change of the discount process. dx from the previous slide, so the discount is copied. Then we have from the previous slide, I just repeat it for your convenience, rt xt dt plus sigma t delta t st dw tilde t. So we substitute that. RT XT dt plus sigma T delta T ST dWt. And here we substitute minus R times D times dt. And the X just remains. So it's minus RT XT dt dt. And this is what we often like in these discounted processes. This term cancels out with this term. So the dt term disappears. And that is often nice because then we are close to the martingale. And that is what we would like to achieve, right? So here we have the discount factor times the interest rate factor times the portfolio value times dt. And here we have it with a minus sign. So they cancel each other out, and this is what remains. So the change in discounted portfolio process is equal to sigma t dt delta t st dw tilde t. And this means essentially that this is in fact a martingale under p tilde. So the discounted portfolio process, little t from 0 to capital T, is a martingale under p tilde. So that's nice. That's nice. And we can work with that. Now let's use that and let's apply what we know to the European call option. And the European call option, you remember at final time, you for the call, you have the right to buy stocks for K. And when ST is larger than K, you make a profit because you immediately, you buy your stock for K, you immediately sell it on the market, and then the profit is ST minus K. And that plus here stands for the maximum of the argument and 0, right? So this is when the stock is less than K, we will not use our contract. So the contract is essentially 0. So this stands for the maximum of ST minus K and 0. That is the option value at final time. Now, what we would like to know is, of course, the option value at time 0, because that is the money that we ask for our option as a writer. And the writer sells the option. The writer should set a price for the option. And the option price is the value at 0. And we often call that also the premium. So the aim in option pricing, one of the aims is to find the premium of the option or the price of the option, the fair price of the option at time t0. And in fact, we are interested in the option value at any time prior to the final time, prior to the maturity time, little t less than t, because at t we know it, it's the payoff. Well, this is a fair price, we say, and the fair price is obtained using the idea of hedging, or the idea of a self-financing portfolio, the idea of a hedging portfolio X, our X that we have just seen, and we also call that a self-financing portfolio. So we would set up this portfolio at time 0, and we would not add money to it, and we would also not extract money to it. It should be a portfolio consisting of money and stocks, and that portfolio is rebalancing itself over time. So there are some stocks bought from the money in the portfolio, and sometimes some stocks are sold from the money in the portfolio, but it remains a total sum. And the aim is that at any time from little t to capital T, the value of the portfolio is equal to the value of the option. And I already mentioned, the writer has sold the option, that can be the ID, sold the option, received some money, V0 for it. And the aim is to have a portfolio. The writer should have a portfolio X, and that portfolio is partly in stocks, delta stocks, and partly in the money market. And by rebalancing the delta, by always changing the delta, it should, at any time, that portfolio process should be equal to the value of the option, and particularly at final time, the value of the portfolio that is owned by the writer of the option should be equal to the value of the option that is owned by the holder of the option. So if there is money in the option, then the money should also be in the hands of the writer in the form of the portfolio process. That is the idea. For any time, they should be the same. And particularly, and not only these two values should be the same, but particularly the discounted value should be the same, right? We can multiply left and right hand side by the discount process capital DT. So at any time, the discounted portfolio process should be equal to the discounted option value. So let's use that. Let's use that for this call option here with this particular payoff. And so we have seen that the discounted portfolio process dt xt, little t between 0 and capital T, it is a martingale under this risk neutral measure P tilde. And we can benefit from that. That tells us essentially that the discounted portfolio process at time t should be equal to the expected value under the P measure, P tilde measure, and P tilde expected value under the P tilde measure is denoted by this expectation operator with a tilde on top. So the expectation under the P tilde measure of the discounted process, the discounted option value at final time, given the filtration up to time t. This is the definition of the martingale. We are on the P tilde, the discounted option that at time capital T, with the filtration up to time t, that is in fact the discounted option value at time little t, and that should be equal to the discounted portfolio process at little t. Now, if we remember, the discounted term is e to the power minus the integral from 0 to t rs ds. And this is the same for capital T. So if we bring this term, it's FT measurable term. So if we bring this term to the right-hand side and we bring it under the expectation and together with this discounting at time t, it gives us in fact under the expectation sign e to the power minus the integral from capital 0 little t to capital T of RU du times the final value here, the final value, the value of the option at final time, which is the payoff, the maximum of ST minus K and 0. And that is then, in fact, the option value at any time little t, at any time prior to the final time capital T. So we have a closed form expression for our option value at any time, particularly also at t is equal to 0, right? We can take little t equal to 0, and then we get this. Now, in the next lecture, with this, I close this lecture, but in the next lecture, we will say, okay, let's be under the Black-Scholes world, where R of S is just constant, little r. Sigma of t is just constant, sigma, and alpha of t is just a constant alpha. And under these assumptions in the Black-Scholes world, we can come up with the closed form solution for the Black-Scholes prize. And the closed form solution we have seen at the end of chapter 4, but we promise to derive it in chapter 5. So that is for the next lecture. I thank you for your attention.